we'll go from current slide, and I'll try to find my pen here. All right, a couple things before we get going. Just a reminder, but this I really am preaching to the choir, but this is for people at home, hopefully listening to it. I've got, out of our 7 great students in this class, only one, Uno, has turned in the research papers. So please get those in. We only have about 2 weeks left in the term. There's final exams, which are a little bit longer, but the actual class days are very few remaining. I know we have class this week and next week. And for Tuesday, Thursday classes, I think that's it, because I believe finals start on the Tuesday of the following week, 2 weeks from today. So I have to have those papers in this week or next week. Otherwise, you lose points if they come in after that. Okay. Now, test 1, as I said earlier, I gave those back to the one student who's here, but got the last of those tests in. And test 2, I've got 3 out of the 7. So the other 4 of you, please get moving on those, because we're almost ready for test 3. All right. And then, oh yeah, that's academic, this class. Let me also say this from more of a social responsibility level. Today is runoff day from the primaries. Did you know to vote today? All right. Have you already or not yet?
I haven't been yet.
Okay, yeah, me either. I'm going after work today, but I teach until 5:30. I have office hours until 6, and then as soon after 6 as I can get away, I'm heading to the polling station to cast my ballot before the day is over. And Evan's here. So I was just harping on, please vote today. Primary runoff day, please vote. Typically on things like this, if they get 20-25% of the voters to vote, that's it. So guess what? 11% of the voters are deciding who our representatives or the candidates are. That's not much of a democracy. So please, please vote. I say it this way: if you don't vote, I think you lose the right to gripe. So don't even let me hear you complain. But if you vote, you have every right to gripe. Whether it's your candidate that you're griping against or the other candidate, you have a right to gripe. Otherwise, hang it up. Okay. So please vote. Please. Okay. Enough of that. That's the paid political advertisement for the day. Unpaid. All right. Any questions on anything we've done so far? Okay. We're in chapter 3, which is determinants, and we're on in section 3.3, properties of the determinant. And we had just said that a square matrix is invertible or non-singular if and only if its determinant is not 0. In other words, if the determinant is 0, the matrix is not invertible and is singular. Okay? So, the question is, which of these matrices has an inverse? This is example 3 on page 122. Oh yeah, thank you. You can't see that? Huh? What's wrong with you? Now, I'd reminded myself 2 or 3 times. I'll turn that on before you start talking. And of course I did. Okay, let me get my pen set up too. All right. Here's 2 matrices. It almost seems like we did this one, but I guess we didn't. Tell me if we did. 0, 3, 3, going down for some reason today. 2, negative 2, 2. And negative 1, 1, negative 1. Or B is 0, 3, 3. 2, negative 2, 2, and negative 1, 1, 1. Two awfully similar looking matrices, one entry different. Are both of those, neither of those, invertible? That's the question. Which of the matrices has an inverse? Certainly you could do a determinant and determine. But there is an easier way on this one. Remember, other things is, remember we teaching 4 different math classes, and we talk about some of the same stuff in all of them. We have talked about linear dependence and independence, right? Or have we? No?
I don't remember that.
Okay. Well, I know we talked about in 2 by 2 matrices, if one row or column is a multiple of another one, then it's not going to have an inverse, right? They're not linearly independent of each other. And that pertains on one of these. Which one?
The one on the left.
One on the left. This column here, this column is a multiple of that. Minus 2 times this gives you this. So guarantee this one will not have an inverse. Can't guarantee that will, but of the two, that one is the one most likely. Okay? And Travis is here. All right. Now, the only way, okay, so we can say off the top, one on the left will not have an inverse because 2 of the columns are multiples of one of the columns is a multiple of another one. The second one, for a 2 by 2, that says it. If you don't have 2 that are multiples of each other, yeah, then it's fine. But on a 3 by 3, you can't guarantee that. So we do need to take the determinant of that. And how do we? There's several ways we can do it. How would you suggest? To the determinant of the second one. Okay, is that what you want to do?
Yes.
Okay, well, let's expand then. Okay. So what I'm going to do is take out that bracket and just rewrite the first 2 columns. Yuck! This thing is doing so weird today. Okay. 0, 2, 3, negative 2, and, oops, I'm looking at the wrong one. 0, 2, 3, negative 2, and 3, 2. Okay. I'm going to close it in as if it's a matrix, but it isn't. It is, but it's a augmented or expanded or whatever. So, can we do our down diagonal? What does that first one give you? 0. Second one? 6. So the determinant of this matrix, I'm going to call it B, okay, is 6 minus 6. Okay, that doesn't look good, does it? Okay, then let's do our up diagonals. Okay, only it's a minus because it's up. Minus 6. It would have been a 6, but it's negative 6. And that up diagonal is 0. And that up one is minus 6, and that gives you negative 12. Yes, it has an inverse. It could be any determinant in the world except 0. It'll have an inverse. If it is 0, no, not an inverse. Okay. So the second matrix has an inverse. It is non-singular matrix. Now that leads to the next theorem, 3.8. how do you determine the determinant of an inverse matrix? Okay? And I think we saw this in the discovery. Did we do that last time? I think we did on the side of the page. This says if A is an n by n matrix, n by n matrix, okay? Other words, it's a square matrix, okay? Has to be square to even determine. And it is invertible, okay? Then the determinant, and I don't like using DET, so I'm going to do it this way. I have nothing against, it's just more writing to do, and I'm just that lazy. Determinant of the inverse, if it has an inverse, the determinant of the inverse is 1 over the determinant of the matrix. So here's where inverse of a matrix does produce an inverted form, okay? The determinant of a matrix is the inverse is 1 over the determinant of its inverse, and vice versa. Okay. Now, the proof of this is fairly straightforward. If it's an invertible matrix, then you know that A times A inverse is equal to what? If it's invertible, what is the product of A times A inverse? Okay. The identity matrix I, very good, okay? Now, from way back in the last chapter, or not last chapter, earlier section, we had a theorem that said that if two matrices, the product of two matrices is another matrix, then the determinant of the product is the determinant of the product. The product of their determinants is the determinant of their products. Okay? That was 3.5, which was, it was early in this section. If A and B are square matrices of order A, then the determinant of a product is the product of the determinants. Okay? So, the product of the determinant of this product is A times the determinant of A inverse. And that's equal to the product of I, the determinant of I. But do you happen to know what the determinant of an identity matrix is? The determinant of I. 1. It's the product of the diagonals, and all the diagonals on the identity matrix is 1. So that's going to be 1. Well, then it follows from this that the determinant of A inverse would then have to be 1 over the determinant of A. Yep. Shows it. Okay. Pretty simple one. All right. All right. To move to, I can hold it for a little bit longer. Okay? Move to example 4. Okay? Find A inverse for this matrix. Determinant of A inverse for this matrix. A. One, 0, 3, 0, negative 1, 2, and 2, 1, 0. Okay. Now, we want to know the determinant of its inverse, and we're given the matrix. How would we determine that? There's two ways to do it. Give me at least one way. You don't have to give me the answer, just how to do it. Second, you can row reduce that with the identity matrix, augment the identity matrix onto it, row reduce it, and come up with the inverse, and then take the determinant of it. That's certainly one way to do. I can tell you're a hard worker, okay? That will serve you in good stead. But yeah, never mind. Okay. What's the other way?
You could expand and find the determinant.
Find the determinant of A, and then,
Put 1 over.
yes, do the reciprocal of that, which will be much easier, I think. Because number one, row reducing that thing is going to take a while, and there's no guarantee it's going to be pretty numbers at the end. These are pretty simple numbers. And then you have to take the determinant of some pretty complex looking numbers, which could have fractions and other things in them. You may not want to go there. But with this, not too bad to take its determinant. So what we'll do is you want to expand it, I thought I heard you say. So I'll get rid of that and expand. And we're going to do the determinant of A, and we'll expand it by doing 1, 0, 0, negative 1, and 2, 1. Okay? Now that's one way you could do this. Another way, of course, is pick any of those rows or columns that has a 0, and every one of them has a 0, and you could just do the expansion that way. About 6 of one, half dozen of the other. This is pretty easy to do, though. So the determinant of A would then be, let's do the down diagonal first, and what does that give you? 0. Whoops. Whoa. Positive 6 minus 2, 0. So that's equal to 4. Well, that's the determinant of A. What does that tell us about the determinant of A inverse? 1/4. So the odds are that was going to come up to be a matrix with a bunch of fractions in them, that the determinant would wind up 1/4. So I think I'm glad we did it this way. Works pretty easily. So the determinant of the inverse is 1/4. You don't really care what the inverse is in this problem. You just want to know its determinant. All right. Now, we're going to go back to something we've been building on and continue the building process. Okay? And what I mean by this, I cannot get this to go down, okay, is we've been talking about what are some conditions for equivalent conditions for a non-singular matrix. What makes a matrix invertible or non-singular? And we started with a few, I think maybe 3 or 4, and we've been building on them ever since. So let's continue that thing. What we got here is A is an n by n matrix, square matrix, got to be, okay? Then all these statements are equivalent. Okay, first, A is invertible. Invertible. Okay, I can't write. Okay, now that also means non-singular. So that's not a separate one. That's just another way of saying it. Okay, invertible or non-singular. Okay, now an equivalent statement to that is this one, that AX equal B has a unique solution for every n by 1 column B. Okay, every one has a unique solution. That B happens to be the 0 vector, then it has a unique solution, which would be all zeros in A. Have to be. well, actually, not, sorry. Then x's will have to be all 0. Because if it's invertible, it can't have all rows of zeros. So the x vector would be the trivial solution, would be the only solution if b were all zeros. That's what I meant to say. Okay? Now that's coming up right now. That's the third one. Is ax equal to the 0 vector, that's a vector now, has only the trivial solution. Okay? That if ax equal to b and b is anything other than the 0 vector, for any b you get, that has a unique solution. Okay? You can't confuse it. You can't fool it. You can't make it so it won't have a solution. It will have a unique solution every time. In other words, no parameter set. No t's or s's or other thing. Unique solution. x1 equal this, x2 equal that, x3 equal that. For any b you put there. And if you put all zeros, it'll have the trivial solution. x1 equals 0, x2 equals 0, x3 equals 0. Okay, that's another equivalent expression. Here's another one. A is, and this is what Evan was talking about, is row equivalent to the I of the same size, I sub n. The last one we added is that A can be written, okay, as a product of elementary matrices. Elementary matrices. And now we add a new one to it. The determinant of A cannot be 0. Okay? That is the new one. If determinant of A is not 0, all the others hold. If any of the others hold, all the rest of them hold, including determinant can be 0. All right, so let's go. Y'all got it? All right, to move on? Okay. Let's do example 5. Which of these systems has a unique solution? Okay. 2x2 minus x3 is equal to minus 1. 3x1 minus 2x2 plus x3 is equal to 4. 3x1 plus 2x2 minus x3 is equal to negative 4. Or 2x2 minus x3 is equal to minus 1. 3x1 minus 2x2 plus x3 is equal to 4. And 3x1 plus 2x2 plus x3 is equal to minus 4. So which of those systems has a unique solution? Or do both? Or do neither? This is kind of a sneaky question in one sense. What would be your first step to solve that? Either one of them.
As far as like checking to see if either one of them have determinant set.
Okay. You're going to get the coefficient matrix, right? Either way you do it, you're going to do a coefficient matrix. What would this one be?
0, 2, -1, 3, -2, 1, 4, 3, 2, -1, 3.
Yeah. Same type thing, only a plus number, right? Okay. Now let's think about those a moment. Have we seen those matrices before? This was the column 0, 3, 3, 2, negative 2, 2, negative 1, 1, negative 1, 0, 3, 3, 2, negative 2, 2, negative 1, 1, 1. What's that?
You thought this is a multiple.
Aha! This column is a multiple of that. Same multiple we had in the last example. And so this one will not have a unique solution, but we already did the determinant of that matrix, remember? Came out negative 12, I believe. So that will have a unique solution. And I asked you for what that unique solution is. It just said which of these will have a unique solution. That one will, because its coefficient matrix has a determinant that's not 0. So therefore, it will have a unique solution. Okay? By 6 combined with 2 from above. And they went back and did the 2 coefficient matrices, even though they're the same one they did in the previous example, just across the page, okay? That determinant was 0, that determinant was negative 12. So we know that one has a unique solution. May not know what it is, but we know it has a unique solution. Because if the determinant's not 0, then that's number 6. By number 2, AX equal B has a unique solution, no matter what those B's are. Okay? And we have it. Okay? Now, another feature, property of determinants, deals with the transpose of a matrix. Now, someone remind me what a transpose of a matrix is. Yeah, flip the columns and rows. Okay? Now, if we're talking about, and you can do that with any size matrix, remember? A 3 by 2 will flip and be a 2 by 3. That's a transpose. That's perfectly fine. But if you're talking about the determinants of the transpose of a matrix, guess what? That matrix has to be square. Okay? So theorem 3.9 says, if A is a square matrix, okay, then the determinant of A is exactly the determinant of the transpose of A. Okay? Now, they didn't do a proof on this, though it's kind of easy to imagine. Okay? Because if you imagine this square matrix A with so many rows and columns, say number blah, 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 and then you do the transpose, that row becomes this column, this row becomes the second column, you go, I don't like that. Okay? And then you think about the fact that the determinant of a matrix, if you start in any row or any column and do the cofactors and the minors and all that kind of mess, any row, any column, that gives you the determinant, right? Well, guess what? If you pick this row here, then pick that equivalent column there. It's only the same. The numbers are the same. And you'll come out exactly the same thing. So the determinant of a matrix is the same as the determinant of its transpose. Okay? And what they want us to do in the next example, example 6, is to show that. It isn't a proof, it's just showing that it's true for this matrix. So here's matrix A. 3, 1, negative 2. 2, 0, 0. And negative 4, negative 1, 5. Okay? Now, I want you to tell me what A transpose is. 3, 2, negative 4, 1, 0, negative 1, negative 2. That's a 0, sorry. Making fun of my writing, I can tell. Okay. 5. Okay. Now, let's do determinant of A. How would you want to do this one? Say again?
Just to expand, take the determinant.
A little louder.
Expand.
Okay, expand the next two. Certainly doable. Certainly doable. Okay. Okay, I'll wipe out that and do this. And write down 3, 1, 2, 0, negative 4, negative 1. Okay? And then let's down diagonal. 0, down diagonal. Down diagonal. 4. Up diagonal. Up diagonal. And 0. Okay. And then up diagonal. Say again? I couldn't hear. Minus 10. Okay. So that's equal to negative 6. Okay. Now, okay, let's do the other one. You want to do the same method? Take the determinant of A transpose. Okay, sorry, I maybe should have written that down. I'll do the same method or something different? Same method, okay. Wipe that out and repeat the first two columns. 3, 2, 1, 0, negative 2, 0. Okay, down diagonal. Down diagonal. Second. 4. Down diagonal.
0.
0. Okay. Up diagonal.
0.
Up diagonal.
0.
Up diagonal. Minus 10. Looked like the same thing to me. Minus 6. Okay. Now, I was just a little surprised that you chose to do that method, though it's perfectly fine. Absolutely fine. Here's how my first inclination would have been, is when I saw that row with 2 zeros in it, let's do an expansion along that road. Start with the 2. And what position is it in? A negative position. That would be a negative 2 times, and wipe out that row and that column, and then do the cross product here. What do you get? 5. 5 minus 2, because minus times minus is plus, but we're going up diagonal, it's negative. So it'd be a minus. So 5 minus 2 would be 3, and that gives you negative 6. You paid your money, take your choice, either one of them works. Same thing with that, only this time, I'm going to expand down the second row, because same thing. So we're going down this way. And what position is that 2 in? Negative position. It would be a negative 2 times. Wipe out that row and column. And what do you have? 5. Minus 2 is 3 equal negative 6. Identically the same. Same process, same wipeout, same everything. Because the rows and columns have just been interchanged. So everything gets interchanged. And it's negative 6 both ways. So either way works fine, and you got negative 6. They did the same as I did, expanding by cofactors. The first and second row and then the second column. and you get identically the same numbers. All right. Now, are any of you heading toward electrical engineering? No? Okay. It's not the only place, but I know electrical engineers use Laplace transforms for something. I don't know what they use them for, but I know they use them for something. A class I took in Laplace transforms when I was, I think, an undergraduate, it turned out that there were very few math majors in there. It seemed like most of the people in the class were either physics majors or electrical engineering majors. So I know they must use them for something. But anyway, the little blurb at the bottom of the page is talking about that. So, hint, hint. Laplace, who in the world was he? Maybe a good paper topic, huh? Or, how did he come up with this transform? Or, what I was suggesting, how is this transform used? There's at least 3 different paper topics here, but systems of the linear differential equations often arise in engineering and control theory, and electronics uses, what do they call it, PLCs? What does that stand for? The C is controller, product line controllers or something, but I've heard the term before, and so I know they use it a lot. And these guys look like they could easily be electrical engineers. Whatever. So let's do homework exercises 3.3, any of the odds 1 through 5. And by the way, the odds have their answers in the back of the book, but also you can see calcchat.com for worked out solutions for the odd number exercises in case you work it out, you check your answer, you get the wrong answer, you can't figure out how you got that answer, the wrong answer, then you can go to calcchat.com, you can see it worked out for those odd number exercises. Then do any of the odds of 7 through 11, either 13 or 15 or both. Any of the odds 17 to 23, and any of the odds 25 to 29. Then any of the odds 31 to 35, 37 to 43, 45 to 49. You can do 51 if you'd like, and then either 53 or 55 or both if you choose. The 57's a proof. If you want to try that, you can. It's probably not too bad. 59, 61. So I'd say any of the odds 59 through 63. The 63 is a proof too. So 59 or 61 for actual problems. 63 a proof, whether you want to do it or not, you choose. 65 is a true false. Understand why that's true or false. Then there's a writing one, 67, that might give you an idea of a paper topic. A proof, 69. And then, here they do it again. It sort of irritates me. They now define a new kind of matrix. Why didn't they do this in the text if it was important? These are called orthogonal matrices. Okay? To determine whether a matrix is orthogonal, an invertible square matrix is orthogonal when the inverse of the matrix is equal to the transpose of the matrix. That's called an orthogonal matrix. So number one, they've got to be square. Okay? You can't have an orthogonal matrix. It's not because you can't have an invertible matrix. It's not square. Sorry. So, you can do any of the odds 71 to 75. And then 79 is also the 77 is a proof that has to do with orthogonal matrices. And then 79 is a problem with that. And 81's a proof. All right. I didn't say it was 81 proof, though. Okay. All right. Ready for 3.4. Applications of matrices, which is the last section in the chapter. Okay? Which means when we finish this, it will be test time again. Okay? And I did say this earlier, if not everybody was in here, I've only gotten one uno out of 7 research papers in from this class. I did get all of your first test in just this week. Did I give you your first test back? Okay, let me do that for you. Just happen to think. And Evan, did I give yours back?
Yeah, test.
Yeah, test 1. I did. Okay, I couldn't remember. No. Okay, here's test 1. Okay, because you came in after I did that. All right, and I just got another test 2 in, so that's good. Now more than half of you turned in test 2. Okay. So please get your research papers in. You only have 2 weeks. Okay? You have this week and next week. The following week, I think, Tuesday, of the following week is the first day of finals, if I'm not mistaken. Okay? So that means to get full credit on the paper, get it in this week or next week. If you wait till finals week, you're losing points. And by the way, this week, you still get that 1 bonus point. Next week, 0 bonus points. Following week, negative. Not bonus points. Okay? So please get them in soon. All right. So we're going to look, maybe not all applications of determinants, but some of the applications of a determinant. Okay? And the first of these is defining a new concept. It's called the adjoint of a matrix. And there is a useful application of this, even though it seems like sort of a pain in the neck to do. Okay? So far in this chapter, we've studied procedures for evaluating and properties of determinants. In this section, we'll study an explicit formula for the inverse of a non-singular matrix and use that formula to derive a theorem known as Cramer's rule. You'll then solve several applications of determinants. And some of them are pretty fun and easy and surprising, maybe. Okay, way back from 3.1, the beginning of this chapter, we talked about cofactors and all that kind of stuff. Okay, so let's just remind ourselves. Okay, a cofactor Cij of a square matrix A is defined as plus or minus 1 raised to the I plus j times the determinant of the matrix attained by deleting the ith row in the jth column. So the matrix of cofactors of A has a certain form. Okay? Well, it seems really awkward. Okay? C11, C12, C13, ... C1n. That's just an n by n matrix. Yeah. C21, C23, C222, C23, ... C2n. C31, C32, C33, ... to C3n. ... down to Cn1, ... down to Cn2, ... down to Cn3, ... everywhere ... down to Cnn. Even though our president doesn't like it. Okay, never mind. We don't have to go there. Okay. That is the matrix of the cofactors of your original matrix. Okay? Now, that's the matrix of the cofactors. The transpose of this matrix, which you take this thing and transpose it to make it C11, C21, C23, ... down to, wait, I said that wrong. C21, C31, ... down to Cn1, C12, C22, C32, dot, 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 down to CN2, C13, C23, C33, dot, 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 down to CN3, dot, 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 down to C1N, dot, 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 down to C2N, dot, 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 down to C3N, and then dot, dot, dots, and dot, dot, dots, and dot, dot, dots everywhere, dot, dot, we'll get to CNN. Okay. That will be the, and those are dots, not minus signs, by the way. Oh, that is going to be what we call the adjoint of the original matrix. Okay. First, you have to do all the calculations to find the cofactors. Okay. Then you transpose that matrix, and that becomes the adjoint. Oh my word! Why would you ever want to do that? Think how many operations is involved in that. This is called the adjoint ADJ of the original matrix A. We didn't even write down what A was. Okay? So, we're going to do that for example 1. Okay? So I'm going to have to erase this. Is that okay? Just remember the steps that we did. Okay? So here is matrix A. -1, 3, 2. 0, -2, 1. And 1, 0, -2. Sorry. Goodness, I'm just running out of steam completely. And why it's just suddenly hit, I don't know. All right. Now the first thing we're going to do is do the matrix of the cofactors. Okay? So, not a super pleasant thing, but it's doable. Okay? All right. So, we're going to start with the 1, 1 entry here. It's a -1. What's the sign of that position? Positive. So it's going to be a -1 times the determinant of what's left. And what would that be?
4.
Yeah. 4, yeah. 4 minus 0. So -1, so that would be a -4. Okay? Oh, wait. Sorry. I'm sorry. I always do this. It's such an awkward thing. The cofactor is not counting the sign there. Okay? The cofactor is the sign of this position times that. Not counting the number there. The number is immaterial. It's the sign of the position times that matrix. Sorry about that. The sign of this position is positive, and then you do 4. So that becomes 4. What I was doing was the minor. Well, not the minor. It was the whole product. And that's not what they're asked for here. The cofactor is just that. Okay? Now, we have to do this for every one. So, and we're not dealing with the numbers themselves, just the signs and the deal. I thought I erased it all, sorry. All right. All right, let's go to this position. What is the sign of that position? Negative. That's all we're interested in, is the sign. Then we do the determinant of the remaining part. And what is that? -1. So it's negative. A -1 would be a +1. Okay? So we'll wipe out those. Okay? Then we'll do the next one. What's the sign of that position? Positive. And then what do we have when we do that? Okay, 0 minus a negative 2, and it's a positive position, so that would be 2. Okay, now we'll go to, goodness, my stomach's growling. I don't know what's going on here. Okay, go to this one. It doesn't matter what the number is, that's immaterial. What's the sign of that position? Negative. And then you do the minor there, and what does that give you? Okay, it gives you a positive 6. Because this gives you a minus 6, that's a minus position, so you get a positive 6. Okay? This is such a pain in the neck to do. It's so tedious. I just lost my 0. Okay. That's nothing. Who cares? Oops. It's a 0. Okay. So let's go to this position. What's the sign of that position? Positive. And then let's do that. And what do we get? It's 2 minus what?
2 minus 2.
Yes. And what does that give you?
0.
0. A positive 0, by the way. No, I'm just kidding. It doesn't matter what sign it is. Okay, yeah, that gives you a 0, and that's okay to get a 0. It's fine. Okay, let's wipe out those. And let's go to the next position, which is this one. What's the sign of that position?
It's a negative.
Negative. And then we'll wipe out that row and column, and what do we get? Second? 2? Okay, this gives you a 0. That one, right? Minus a 3. It's minus 3, but that's a minus position, so that gives you plus 3. Okay. All right. So let's get rid of those construction lines and go to the next one. This is so much fun, isn't it? Okay. This one, what's the sign of that position? Positive. So we'll go like this, and what does that give you? Okay, that's 3 minus a minus 4, 7. Okay, and that's a positive position, so that's a 7. All right, go to the next one. This is tons of fun. Okay, all right. Now, doesn't matter, it's a 0. We're just interested in the position. And what is the position there? The sign of that position? Negative. So then we do the determinant of what remains, and what is that? Okay, a negative and negative 1 is positive 1. Okay, we're done with that one. And we do the last one. This one's the one we've been dreading, isn't it? Okay, what's the sign of that position? Positive. And what remains? Just 2. There is the matrix of the cofactors. Okay, remember the cofactors don't multiply that number in, they just use the sign of the number and the cross product, you might say. Okay. So there is our matrix of cofactors, 4, 1, 2, 6, 0, 3, 7, 1, 2. Okay? So what would be the adjoint of that matrix, of this matrix A? Well, the adjoint of matrix A is the transpose of the cofactor. So let's do, we'll call this C, and C transpose would be what? 4, 6, 7, 1, 0, 1, 2, 3, 2. Now that is also the adjoint of A. Okay? That is the adjoint of A. 4, 6, 7, 1, 0, 1, 2, 3, 2. All right. Yuck, what a pain in the neck to get there, right? But it wasn't hard, it was just tedious. So what do we do with that? Theorem 310. If A is an n by n matrix, it's supposed to be an n. The pen just sort of does its own thing. Okay. N by n invertible matrix. Okay. Then the inverse of A is equal to 1 over the determinant of A multiplied by the adjoint of A. All right. I think I like row reduction of the identity matrix a lot better than this, okay? But again, this is something that perhaps is easier to program than the other, okay? So what we do, take the determinant of A first, 1 over that, because that relationship you have there, and then multiply it by the adjoint of A. So you got by determining the cofactor matrix and then transposing that. Okay. I really want to do this, yes. Okay. Now, they have a proof here that goes on for quite a way, but it's a pretty good little process. Okay. Now, excuse me. Swear. What's wrong with me, but I'm just clogging up like crazy. Do you remember when we first started doing inverse matrices, there was a little rule that made the 2 by 2 so easy to do? You remember that? You did 1 over the inverse of the 2 by 2 matrix, which it was real easy to do. And then multiply that by a new matrix. And what we did, we reversed the diagonals and negated the off diagonals. 2 by 2. Remember that? Okay. Now let's think about what that was in this sense. So let's imagine this was our 2 by 2, not a 3 by 3. Okay? Its determinant would be 2. So this would be a 1 over 2 here. Okay? And then we would do reverse. Am I saying this right? Yeah, I think so. Reverse the these two and negate those. Okay. Well, let's see. What is the cofactor for this one? What's the sign of that position? positive. Wipe out this and this, and you're left with a negative 2, right? Okay. So that's what you would put up here, negative 2, right? Hey. Actually, okay. Let's actually do what I'm saying. All right. I'm going to make up a new problem here. All right. Now we've already said that we're going to take the determinant of that and divide by it. And the determinant of A okay. All right. The determinant of A was 2, right? Isn't that what we said? Okay. So our final answer is going to be the A inverse is going to be 1 over 2 times something. Okay. Now, what we were doing was taking finding the cofactor matrix of this one. This is really simple. The sign of this position, right? Positive. Wipe out row and column times it. That gives you a negative 2, right? Because the sign of this position is positive, so you get a negative 2. Okay? Sign of the next position is what's the sign of that position?
Negative.
Negative. And then it's a negative 0, right? So it's a 0. So that becomes a 0. Okay? And then for the third one down here, what's the sign of that position? Negative. And its cofactor is 3, so it's minus 3. So that's what we put here. And then the sign of the fourth position there is positive, and its cofactor are the negative 1. So that'll be a negative 1. Now we're going to take that and exchange rows and columns. So this will become a negative 2, negative 3, and a 0, negative 1. Right? Now, we've done the things according to this, and then we take that becomes the adjoint of this UA, and then you multiply this with it. Well, let's see what we wound up doing. We exchanged the 2 diagonals, and we negated the others. That's exactly what we were doing this before, but it's so simple on a 2 by 2. We just did that. Okay, so sorry. The reversal comes from the sign is the same with this, so this moves up here, that one moves down there, because these are both positive, so that's all that happens there. What happens with this is they move and negate because they're negative, but then they move back when you transpose. So you wind up just negating. So you reverse the main diagonal and negate the off diagonals. And that comes from this very practice we did. Okay? I just wanted to show you, they mentioned it in the book. These come out the same thing, but it's so much easier to remember the rule for the 2 by 2 than to do the cofactor. Okay. So let's erase all this and do example 2. Here's matrix A. Negative 1, 3, 2. 0, negative 2, 1. 1, 0, negative 2. Okay. Now, that's matrix A. Does that look at all familiar? Yeah. That was the matrix in example 1. And what was the first thing we're going to do if we're going to use the adjoint to find A inverse? We need the adjoint of A. And we calculated it in example 1. So let's just retrieve it, okay? The adjoint of A, remind me what it was? 467, right? 101 and 232. I mean, we could do it all over again, but we just did all those steps. That's the adjoint. And what do we do with that? Well, the A inverse is 1 over the determinant of A times the adjoint of A. Okay, we've got the adjoint of A. All we need now is the determinant of A. And that's not too bad either, is it? Let's erase that. I assume you're wanting to do your favorite. Okay, so that would be a -1, 3, a 0, -2, and a 1, 0. Okay? So, first down diagonal, what does that give you? -4. Next down diagonal, +3. Next down diagonal, 0. First up diagonal, +4. That wipes out the -4. Okay. Next up diagonal, 0. Next up diagonal, 0. So what's the determinant of A? 3. Okay. So your A inverse is equal to 1 over 3, that's the determinant of A, times 4, 6, 7, 1, 0, 1, 2, 3, 2. Now that's perfectly all right to leave it in that form, but if you wanted to multiply that through, that would be 4/3, 2, 7/3, 1/3, 0, 1/3, 2/3, 1, 2/3. There's the inverse of A. Now, this was pretty easy because we had already done this. Okay? Now, remember what we went through to do that, though. Do the cofactor matrix, do the, we again use the, goodness gracious, I'm going blank. And transpose it. Okay. We did the cofactor matrix, and then we transposed it. Okay. Now, admittedly, I mean, the cofactor matrix was not impossible. It was fairly straightforward, especially a 3x3 is not that bad. So it wasn't, entirely miserable to do. And then transposing is really easy. So, whereas taking that original matrix and doing the row reductions, especially when you wind up with a bunch of fractions in there, that might be a place easy to make errors. Because factors wasn't. Too bad the numbers came out pretty nice, and no guarantee they always will, but they usually are going to come out pretty nice, okay? And your whole introduction to the fractions comes with the determinant, okay? Because it's 1 over that determinant. Now, especially if that had come out 1 over a negative 12, then these could have really been messy looking fractions. You know, and the more likely that is to be something like that, and the bigger that denominator, which here would just be the bigger the number would be, that'd be messy, and I can't imagine doing your expansion of this, you know, with the identity matrix here. Now, if that determinant comes out 1, that's going to be a piece of cake, okay? But most of the time it doesn't come out just 1 or minus 1. Those are the easy ones. Most of the time it's going to come out some bigger number, and it could be 53 minus 27, you know, and then you're going to have a real messy thing. So it might be that this isn't too bad after all. Finding that the factor matrix and then the adjoint, the transpose of that. So, again, pay your money, take your choice. You've already paid your money, so you figure out your choice. All right, so they did get 4/3, 2 7/3, 1/3, 0 1/3, 2/3, 0 1/3. Now, I love it when they say this, don't you? They say, check this matrix, the inverse of that, by showing that A times A inverse is equal to the identity matrix, and then that is the same as A inverse times A. So in other words, go back to your A and multiply it by this, and then multiply this by that in the other order, and make sure they both turn out i's. I'm sure y'all want to do that, don't you?
I believe you.
Okay, he's easily persuaded. Okay, I do too. Okay. Actually, it turns out being not too awfully bad. All right. So there's one application of determinants. You can use them to find the inverse of a matrix, sometimes without going through the messy calculations that might evolve with fractional forms. And you know they do pop up there. Here's a second application. Okay? And this is called Cramer's rule. And by the way, if you haven't done a paper, which most of you haven't, who in the world was Gabriel Cramer? Okay? Lived way back there, 1704 to 1752. Where were we then? We were colonies, at best. Alabama wasn't even a colony. It was a territory, okay? This is way back. Georgia wasn't a state yet. You know, it became a state during that time. This was way back during the colonial era of the U.S. The first of this, we had 12 colonies, and we got the 13th, okay? So this was way back. So Gabriel Cramer used determinants to solve a system of n-linear equations and n variables. This rule applies only to systems with the unique solutions. You can't get your parametric solutions. Won't happen, okay? So to see how Cramer's rule works, let's take another look at solution described at the beginning of 3.1. And this is sort of a pain, but I guess it's worth it to do. All right. Here's your simple system of equation. A11x1 plus A12x2 is equal to B1. A21x1 plus A22x2 is equal to B2. Okay. Now, back in algebra, if you had a system of 2 equations and 2 unknowns, and there wasn't any easy way to do this, what we would do is pick one equation, multiply Okay, it's called elimination by addition. You choose the variable you want to eliminate, and you do it. So if you're going to eliminate A1, or X1, the variable X1, what you would do was multiply the top equation by A21 and the bottom equation by negative A11. Now the coefficients are the same, you add them, they go to 0. But you wind up with a bunch of mess here. So let's see what you wind up with there. That would be A12 times A21 x2 is equal to A21B1. They do it the other way. I'll change it in a minute. Okay? And then you solve for x2. Okay? So x2 oh wait, no, that wasn't all. Sorry. Let's pause a moment here. Regroup. That's your first equation. Why is that not erasing? I don't know. I don't know. Not erasing at all. I don't know. Okay. That's your first equation. Your second equation would have been a minus A11 A22 x2 is equal to, or yeah, minus A11 B2. Okay? Now, when you add those two together, you see I left off the first part because those are going to add to 0, right? So when you add these two together, you get A12 A21 minus A11 A22 x2 is equal to, I'm going to reverse the order on these, B1 A21 minus B2 A11. Okay? And that winds up with x2 equal B1 A21 minus B2 A11 over A12 A21 minus A11 A22. Now, that's x2. Right? That's what they got. Except they reversed the order of them. They made this the plus and that the minus, this the plus and that the minus. It works out the same way. B2 A11 minus B1 A21 over A11 A22 minus A21 A21 A12. Doesn't matter the order. Okay. Now, they do the same for x1, and it turns out being I think it's A12. Oh, I think they put the B's first. B2. No, they start with B1. So let me start with the same thing. B1 A22 minus B2 A11 over A11A22 minus A12A21. Okay. Now, I didn't do all those, but that's what it comes out being. Here is the interesting thing about this. Notice your denominators are the same, aren't they? And what's more, let's take a look at this. A11, A12, A21, A22. If you look at that matrix, that's your matrix of coefficients, which we've used several times, right? Notice what the denominator is. A11, A22 minus A12, A21. What is that? This minus that. That's the determinant of your coefficient matrix. So x1 and x2, the denominator is going to be determinant of A. That's your coefficient matrix. Okay? Now, let's notice what the numerators are. Okay? B1, A21 B1 A22 minus B2 A11. So in other words, for the numerator of x1, put your b's here and keep those coefficients the same, and that gives you that determinant. Okay? So what I'm going to do, strangely enough, is this. The determinant of B1, B2, A12, A21. And then when you do x2, you keep the x coefficients the same, A11, A21, and instead of the y or the x2 coefficients, you put B1, B2. And sure enough, that determinant is this one. So let's see if that B works. This is B1, A21. Oh, wait. Where we wrong? It's A22. Okay. B1, A22 minus B2, A1. I wrote that wrong this time. Goodness gracious, I can't get anything right. X1, thought I was copying from the book. That's the 2 there. Sorry about that. I was doing the A2. Okay. So now I think I've got it right. B1, X1. B1, A22 minus B2, A12 over determinant of your coefficient matrix. And X22, let's try that one. B2, A11 minus B1, A21. Got that one right over the determinant of your coefficient matrix. This is first order relation. Okay. So that leads basically to Cramer's rule. Okay? So let's do one. Do we have time? Yes. Okay. They're much easier to do in person than to use all the letters. The letters just get crazy. Okay? Here's a system of equations, really easy to do. 4x1 minus 2x2 is equal to 10, and 3x1 minus 5x2 is equal to 11. Okay? Now, you got three determinants to do. The first is real easy. If you want to write it down again, you can. That would be this one. 4, negative 2, 3, negative 5. So let's do that determinant. What would that be?
Negative 14?
Yes, plus 6 equal negative 14. So there's going to be your denominator. Okay? Now, the next one we're going to do is for the x1s, and they call this A1. They call this A, determinant of A, which is your coefficient matrix. Your A1 is when you substitute your B's for your coefficients of x1. So this determinant is going to be 10, 11, negative 2, negative 5. So let's do that one. What's that determinant? You don't have to do it in your head. Just call out to me what to write down. Negative 50, isn't it? Okay. Negative 50 plus 22. And what do you say it was?
Negative 28.
Negative 28. Perfect. Okay. And let's do the A1. A2. And that's where you substitute the B's in for your x2 coefficients. So this will be 4, 3, 10, 11. Uh-oh, I meant to do that. Okay. And what would that determinant be?
14.
Second? 40, yeah, 44 minus 30 is 14. Okay, you're really quick. Okay? So, what's your x1? It's your A1, negative 28, over your A, which is negative 14. And what's that? 2. And your x2 is your A2, determinant of A2, 14 over your determinant of A minus 14, and that's equal to negative 1. Let's see if they work. 4 times 2 is 8, minus 2 times a negative 1 would be negative 2 times negative 1 is plus 2. 8 plus 2 is 10. Good. Do it this one. 3 times 2 is 6, plus 5 is 11. Yep, there it works. Now, is this easier than doing your elimination by addition? Probably not. I don't know, it may be. It's pretty simple, and the calculations are pretty easy. And elimination by addition is going to get a little bit hairy, isn't it? Let's multiply this one by 5 and that one by negative 2. That would give you 20 minus 10x2 is equal to 50. And this will be minus 6x1 plus 10x2 is equal to minus 22. That's kind of hairy, and you still have to do substitution, plugging in and stuff, but you should get the same answer. I don't know. This is pretty easy. Okay. So Kramer's rule might make some of these easier. Now that's a 2 by 2, so it's about a toss-up. Okay. Guess what? You get the 3 by 3s? Uh-oh. 3 by 3s. Well, the other way you could do it is by row reduction. I didn't think of that. But that's going to have all sorts of fractional forms in it. Okay. And kind of messy. So Kramer's rule isn't too bad. Okay. 3x3s? You decide, okay? And they show you that next. Do we have time for it? I'm kind of guessing we don't, because it's just a lot of writing. So I think what we'll do is pause there, stop there. Okay, and we'll start at the top of page 131 next time. Okay? And see what homework exercises you can do in 3-4. Any of the odds 1 through 7. You can do number 9 if you'd like. It's a proof. Number 11, I think, is also a proof. If you've done number 11, you can do 13 fairly easily, I think. And then if you want to do 15, you can. Okay? I'll leave it like that. Then you can do any of the odds 17 to 23. We'll hold off on the 3x3s until we do the next example. So just go through 23 for now. Actually, if you wanted to jump on and try 31, you could. That gets a little messier, but I think you can. And we'll pick up that a little bit later and go from there. All right, any questions? Now, the question I have for you, would there be any advantage to going and picking up the test today, or you want to wait till Thursday? I don't know if we'll be through with the section by Thursday, but at least we'll be far enough along and you'll have it for the weekend. But if you want it now, I think it's copied. So, you want it? Okay. And you can get started. You might not be able to do it all, but you can at least get started. Now, I know I sent it down to get copied. Let me make sure it did. Did I get it back? Maybe I did. Yep, there. There is my original. Ah, there it is. I do have it. Okay. There we go. Okay. And then one time this has been test 2, what I did, I used to try to cram chapter 1 and chapter 2 together to make one test. But it just got so long and tedious, I thought, let's make that 2 tests. And so this used to be test 2, now it's test 3. That's why the smidge on the page I didn't go back and change. All right, good deal. Any questions? Please vote today. Primary runoffs are today, so please remember to vote.